This video continues from the previous one. Now we're going to look at performance index. Now implicitly, humans have got a fairly good idea of what constitutes good and bad behaviour, although they may rarely be particularly quantitative. So for example, if I said to you something was very slow, and you'll notice I've got a target settling time here, then if I did a response a bit like this, you'd say, yeah, okay, that's slow because clearly it's not getting to the target in time. If I said something was oscillatory and I was to do a plot a bit like this, you'd probably say, yeah, that's fairly clear, that's oscillatory, that's probably not very good. What about something's unstable? Well, there's an unstable response, and you say, yeah, that's fairly clear. And what about if I said something is close to ideal? Well, if I had a response that did something like this, then you'd say, yep, that seems to get there in my target settling time, it's not too oscillatory, it's reasonably smooth, that's fairly ideal. But you'll notice I've been relatively qualitative in my statements here. But the key thing is you've got an idea about what is good and bad. Now, when designing a performance index, therefore, you've got to answer some simple questions. What is the performance index used for? And how should the performance index be designed? How can it be used to handle trade-offs, this is quite critical, between optimal and safe or robust performance, because you'll find sometimes they can work against each other. And what performance indices do humans use in everyday life? Because if we understand what we do, we might be able to use this insight in order to get a better predictive controller. So for example, how do our performance indices change as we go from being very young to old? And how do we use that insight? So what's the performance index used for in predictive control? Basically, it's how you go from a concept to an actual strategy. It's how do you decide which input trajectory is best. So your performance index gives you a numeric number that allows you to compare different strategies, and therefore you can choose the one that you think is best. So there we go, the performance index is a numeric definition for best. Now, we do have a problem here, because you're going to define some number for the performance index, but the problem is that this is going to still be arbitrary in a sense. So although you can say, I'm going to define best to be what this performance index says is best, where has your performance index come from? And you'll see that you have to make some relatively arbitrary decisions to get to that in general. So how should your performance index be designed? Well, general guidance suggests that the simpler definitions you use, the better. Because if it's simple, you'll get better conditioned and simpler optimizations. Now, as the optimization is carried out online, you want it to be well conditioned, you want it to be one that converges quickly. Okay? Because there are risks otherwise. So you should only have a more complex optimization and performance index where the benefits of doing that are clear. Now what you'll find is typically users use a quadratic performance index because these give well-conditioned optimizations, they have a unique minimum, and generally they give you smooth behaviors. You could investigate things like one norm and infinity norms, but what you'll find is in general they don't give such smooth behaviors and they can be more sensitive. So human behaviors then. So how do human performance indices change as we get older? So I'm going to use the example of a racket sport again to demonstrate this. A beginner, you can imagine that as a baby or a toddler or someone quite young, has a very simple strategy. Basically, can I get the ball back across the net? I don't care where it goes as long as it goes across the net and it stays in play. So anywhere and anyhow. As you get slightly better, you're going to get a bit more sophisticated. So not only do you want to get the ball back, but you want to do so with some measure of control and direction. Now obviously an expert is far more complex than this. Not only do you want to get the ball back, but you want to be much more precise on how. Sometimes planning several shots ahead in order to create an opening. So what do you notice here? The performance indices that we use as humans change depending upon the context, and that's something you need to remember when you're designing yourself for a real scenario. What scenario have I got, and what sort of performance index is most appropriate? So as we get older and more experienced, our performance indices become more demanding. And you could use the same insight here to many other things that humans do. So modelling and performance, these two link together. Now, the reason that our performance indices become more challenging as we get older is because our internal models of what's going on are better. Basically, we get more experienced, and that implicitly means that the models in our brain of how we move and how things work is better. So what simple insight does that give you? If you've got little experience, or equivalently a low quality model, then all you can expect is cautious performance. So your performance indices have to be fairly simplistic and not asking a lot. Conversely, if you've got lots of experience, or equivalently a very high quality model, then you can have very ambitious performance indices. The fact that you can have them doesn't mean you have to, but it's an option. So there's a key thing there. If you've only got a low quality model, don't expect a very highly defined performance index, because it doesn't make sense. What next? How do we handle trade-offs between optimal behaviour and safe or robust performance? And you'll see this is quite similar. So again, if we use the analogy of a racket sport, a player might use a very complex strategy, not only getting the ball back but being very precise on how, and that's trying to hit the lines and the corners, etc., etc. Another player might have a much simpler strategy of simply keeping the ball in play, for example aiming for the middle. Now, who's more likely to make a mistake? And we're going to assume here that the opponent is passive. And of course your answer will be that the person who's adopting a more complex strategy is more likely to make a mistake, more likely to come unstuck. So in other words, their strategy is less robust. So what have we got? High performance demands are not cost-free. If you want high performance, then implicitly you've got high risk. Okay, so high risk is equivalent to less robustness or less ability to deal with uncertainty, things that you didn't expect, the ball not bouncing quite as you expected, or something else. If you have a low performance demand, but you have a high fidelity model, then essentially you're in a low risk environment, okay? Because you're working well within your capacity, and therefore your strategy is likely to be safe and robust to uncertainty. So you'll see you have choices. If you want high performance, implicitly you're working with a high risk. How many degrees of freedom then do you think you should use? Now, the degrees of freedom describe the complexity of the input predictions, or the variety in the input predictions over which you are going to make a selection. And so you'll see this issue is actually closely linked to the previous discussion on performance indices. So here we've got, there is no point utilizing high numbers of degrees of freedom, that is having a high degree of flexibility in what input trajectories you might choose, if your model is poor. So if you imagine the racket sports player, all they can manage is just about getting the ball back. It's no point planning a strategy of 4 or 5 shots ahead, because they're simply not up to it. Their model does not cope with it. Now, the result of any corresponding optimization would be largely meaningless. That's the key point. So if you've got a poor model, but you use a very demanding performance index and lots of degrees of freedom, the solution you get will not mean very much. Okay, so the useful number of degrees of freedom is actually linked to how accurately you can predict. If you can't predict accurately, then there's no point having lots of degrees of freedom. Now, here's a scenario which demonstrates what I'm going to call an ill-posed performance index, or an ill-posed objective that you might yourself. So you've got a very demanding performance index here, one which says I want you to follow quite a complex trajectory, and in this particular case the trajectory I want you to follow is this red one. Okay, but you're a simpleton, you've not got a very good model, okay, and so the only thing that you can manage is a first order polynomial. So what you're going to try and do is model this red curve using a straight line. Now, of course you can't do it. You'll get nonsense. You'll say there's no way I can match that even closely. And so therefore this is what I would call an ill-proposed performance index. You're basically trying to model oranges with apples or something like that. It's nonsense. You can't do it. An alternative would be, say, can you follow a corner in 50 yards time by turning the steering wheel now? And of course you say, well no, I've got to turn the steering wheel in 50 yards time, not at this point in time. And what you've got there is a mismatch between the degrees of freedom you've allowed yourself when you can turn the steering wheel and where you actually need the turn to take place. So these are examples of ill-posed problems. If you've just got 1 degree of freedom, okay, which is what I've given here, so you've got a straight line or just turn the steering once and that's got to be now, then you can only have simple performance indices and simple targets. Okay, so if you've got low numbers of degrees of freedom, you must have simple performance indices and simple targets, because otherwise what you're trying to do will just not make sense and you could end up with an arbitrary result. Okay, and you'll see time varying targets need high numbers of degrees of freedom. Okay, here's a similar example. Imagine a scenario where you've got a low prediction horizon. So for whatever reason I'm not predicting too far into the future, but I've given myself lots of degrees of freedom in order to optimize tracking within that horizon. So you'll see what I've done here. I've given you a little diagram up the top. I said I want you to model or follow those red circles. Okay, and because I've given you lots of degrees of freedom, and you'll see I've basically fitted a blue line which has gone quite well through it, and you say great, I seem to have done a good job. But the key thing here is I've only done the optimization over a low prediction horizon, whereas in fact I need to model the data over a much larger prediction horizon. So what happens when I look at the whole horizon is this. You'll see that the actual data drifts over here, and so my model is now poor. Now what's caused this problem? The problem is that I've used low horizons. So I've focused all my effort on minimizing the errors over low horizons and assumed that everything will be alright thereafter, and it isn't. Okay? And a similar example might be to optimize the speed of a car looking only, okay, you'll see 50 yards ahead, okay, and I'm driving quite fast, and there's a corner that's just beyond 50 yards. So here you are, you see I'm doing 100 miles an hour, and the corner's 51 yards ahead, but I'm only optimizing, here's the key thing, so I'm only optimizing up to this point here, which is why I'm doing 100 miles an hour. I'm saying, yep, I can do 100 miles an hour, no errors, everything's fine. And I haven't seen the corner, which is 1 yard further beyond. So of course what's going to happen is I'm going to have problems. Now, what are we trying to get at here? These are examples of ill-posed optimizations. The problem you've actually solved is not well thought through. Because you've focused on using low horizons, you cannot fully anticipate the full consequences of your actions. And so the actions you're actually taking may be very poor indeed. Okay, so that's what you need to take away from this. It's an example of an ill-proposed performance index, one which is only focused on low horizons, okay, may take decisions which actually make no sense at all. Okay, and the other thing you'll find here is advanced target information can only be used effectively if you've got a large number of degrees of freedom. What about constraint handling? One advantage of predictive control is that it embeds constraints into the strategy from the outset. So a proposed input trajectory can only be optimal if it satisfies constraints. There's no point coming up with an input trajectory that violates constraints, because you can't implement it and therefore is meaningless. Okay, and you'll find that most control strategies, PID, lead, lag, and so on, they treat constraints as an afterthought. They say, this control strategy gives me good loop dynamics. Oh, I'm going to violate a constraint. What should I do now? So the systematic embedding of constraint information is critical to getting effective and robust closed-loop behavior. So here's an example. I want you to form a PI control law which gives you a good speed of response, a good settling time, and we'll implement it on a tank level control system. And here you see I've given one and it says, yeah, it's not too bad, it's given roughly 25% overshoot, a bit of oscillation, but it's smooth, and if I implement that most of the time, I'm very, very happy. But what happens if you're actually running the depth fairly close to the limit? And therefore, what you find is that this value here is 110% of the maximum. Then clearly you can't get that, and what's going to happen is this will saturate somewhere down here. You'll have a saturation, and what happens when this saturates if you've got a nuclear reactor or something of that nature? Okay, then you could have a disaster, because you could have chemical spilling over the tank. You could have the reactor that you can't cool down and it blows up. So you must include this constraint in the design of the strategy at the outset. Otherwise you could lose control of the process with any number of problem effects. And here you'll notice the underlying control laws may have been good and robust as long as you did not operate close to constraints. But as soon as you get close to constraints, your original designs may be totally useless. So how's predictive control different? Well, the constraints are embedded into the planning. Predictive control will not propose input trajectories that allow a tank to overflow. Okay? And this may result in slightly slower rise times during transients, but at least it will be safe. And predictive control will be aware that inputs are limited to 100%, and thus it will not allow, and here's a key thing, it will not allow you to make earlier decisions which require you to go beyond 100% later. They will basically say, I can never go beyond 100%, so if that means that the current input needs to be slower or smaller, then so be it. So in general, if you embed constraints into the problem at the outset, and with cars it could be an awareness of where the curbs are, it could be flow or power limits in process control, speed limits for robot and so on, then you will ensure that the actual input strategies you design are optimal. Okay? And the other thing is, you'll find that automatically you'll get modifications in the tuning of the loop where required, depending on how close you are to the constraints, which is what happens as you move between operating points. So a simple, well-tuned but unconstrained law may be very effective in a small range where you're not close to constraints, but could be disastrous over a wider operating range when it comes closer to constraints. Another point then, multivariable systems interact, and there are many examples of processes which have large numbers of inputs and outputs. A car maybe has two main inputs, the throttle and the steering wheel, and two main outputs, the speed and the direction. An aeroplane has got numerous control surfaces and moves in 3D space. Chemical reaction could be affected by flow rates of reactants, the heat supply, the pressure, and the outputs could be speed of reaction, production rate, quality, purity, and so on. So a key observation that you need to be aware of is if you have a multivariable process, something with many inputs and many outputs, then often changing a single input will change, here's the key word, all of the outputs. And therefore an effective control law has to consider all the inputs and outputs simultaneously. You can't break them up into this input looks after this output and the second input looks after the second output. They all interact, and so you have to consider them all simultaneously. And anyone who's learnt to fly a helicopter will perhaps realize this best. Okay? The other thing is you'll realize that humans often struggle to develop effective strategies for processes which have a lot of interaction. Okay? We can cope with up to 2 or 3 inputs and outputs. We can learn by trial and error and just about be an effective controller, but not if it goes beyond that. And you'll find the same observation applies to classical control techniques such as PID and lead and lag. They're very good for single input, single output systems, but it's not very easy to come up with a systematic design where there is significant interaction and you've got 2, 3, 4, 5 inputs and so on. And so the advantage of predictive control is that it's a framework that automatically, that's the key word, automatically takes account of interaction. Okay? As long as we express the algorithm in suitable mathematical language and get a computer to do any relevant number crunching. So a summary. We've shown that the key concepts underpinning predictive control are prediction, and we've talked about how and why you might need to predict. We've looked at the receding horizon. We've looked at requirements for modelling, requirements for the performance index, issues linked to the degrees of freedom, which perhaps are a bit more subtle, constraint handling, and the fact that it's multivariable. Now, so far we've done all of these things very briefly, just to set the scene. Okay? And what we're saying is a good understanding of these concepts will ensure that the viewer comes up with a predictive control algorithm that makes good sense and therefore is likely to be effective. So again, we've done this very briefly, and so the future videos are going to discuss these things in more detail and in parts in more rigour. Okay, so this has been deliberately fast just to set the scene, to get you thinking about what are the issues that I need to understand. So in summary, a well-posed predictive control law, the modelling efforts should be focused on the efficacy for prediction, which includes the dependence on the degrees of freedom. So you don't just model for the sake of modelling, but the modelling has to think about, can I use this model for prediction? Does this model show the impact of the degrees of freedom I've given myself? Predictions must capture all the transient and steady state behaviour. It's no good if they just capture short-term behaviour. The prediction class, and this is a subtle one which links to the degrees of freedom, the prediction class should include the desired closed-loop behaviour. You remember, trying to model a sine wave with a straight line was totally meaningless. Well, this is the same concept. It's no point trying to optimize something where the behaviour you want is not included in the class of predictions that you're allowing yourself. Performance indices must be realistic and match to model accuracy. No point having a highly demanding performance index if you've got a pretty poor model. Constraints must be built in from the beginning, because otherwise you can get inconsistent solutions. Efficient computation requires linear models and simple parameterizations of the degrees of freedom.